Right.
Okay, here we go. So let me just start by saying a few words of what I want to do today. So let me just start with taking a compatibility. If you're not an expert, you can just take any matrix group that you enjoy, like orthogonal groups or unitary groups or complex groups, whatever group you like. This is not a big, if you want to think about matrices, this is not a big deal because we're going to be thinking about compactly groups. And you can embed any compactly group in the inside a big enough group of matrices that are reversible. So that's good enough. And then there is a basic problem topology, which is a computation of multiple groups of a given big group. And you can basically spend a semester talking about results in that direction. So let me just say a couple of things. For example, if you take out the unitary matrices and you want to study the homotopy groups, then it's quite well known and it's not too hard to show that these guys stabilize and then the stable homotopy groups are given by the homotopy group of what is called the unitary groups. And moreover, these guys satisfy both periodicity and then these stable groups are either zero or set. So those just to say one well-known result that has to do with what periodicity and K theory. So this actually, although it's easy to prove this stabilization, the blood periodicity is not that easy and is connected to K theory. So there is a lot of stuff going on here. And then you can you can ask similar questions for the orthogonal groups and the reflective groups, and then you can obtain similar results, although the periodicity is different. Anyway, this problem is actually quite reasonable. You have a group that happens to be a smooth manifold, and then there is compatibility with the operations, and you would like to know what you can say about the problem. So when you start to think about that question, there are two well-known results that you can think of, which are the following. I don't know the actual persons that invented this, so I didn't want to put credits here because I was looking around and I don't think I was able to find it, but there are two well-known results that come up to mind when you're thinking about homotopy groups of Lie groups. And the first one is that you don't really need compactness because when you work with a Lie group, you can for homotopy computation you can reduce to the maximal compacts of group if you please. But let me just state everything in terms of compactly group. So the first result, well-known result, is that the second homotopy group of a compactly group is trivial. And then there is another one, which is the one that I'm going to be using today, which is the fact that if you have a compactly group that now we assume is simple, then the third homotopy group is isomorphic to the integer. Do observe that we don't need to ask that the group is simply connected. And the reason that you don't have to do that is because you can reduce it to the case where it is simply connected by passing to the covariance. So this is a nice result. And moreover, you can say something about the generators of a generator for this homotopy group. So this is basically the best possible scenario. You have a group where you can say what it is, and then you can find a generator. So let me just remind you how you can obtain a generator for the third homotopy group of a compact and simple group. So let me just, for simplicity, assume furthermore that G is simply connected. And then what you can do is you can take the Lie algebra, and then with the Lie algebraics, comprehensive algebra, and get the root system. And it turns out that with the root system, you can obtain a generator for the third homotopy group in the following way. So for any, if you look at the root system, for any root in the root system, you can find an embedding of the Lie algebra of SU2 inside of G. So this is basically obtained using the decomposition of G as the Cartan algebra plus the corresponding G sub alphas, and then but that has to be done with the complexification. But then you go back to the actual Lie algebra, and then you for each root you can get an embedding like this. And that embedding is an embedding of the algebra. So what happens is then if you have a homomorphism between Lie algebras and the source group is simply connected, then you can integrate any such Lie algebra homomorphism. So associated to any root, you can find a homomorphism from SU2 to D. But what happens is that SU2 has a topological space in this here. So with any root, you have a map from S3 to D. Okay. Now, if the root, so when you have a Lie algebra, the Lie algebra of that is simple, then and if you endow T, the Cartan algebra with a W invariant form, there are only two possible lengths for the root. And if you choose alpha to be the longest root, then what happens is that the corresponding map is a generator for the clear homotopy group of G. So that's as good as it gets. So you have a computation which is realized by 3 of G is Z. Moreover, you can say how do we compute a generator in terms of the geometry of the namely the root system. Now, if you change another root, then if you don't take the longest root, then you would get a multiple of this guy, and the multiple will be either 2 or 3. So, so that's as good as it gets, right? Or at least that's what I think. In this minute, this is my opinion, is as good as it gets. So you have a representation, and you can say how to obtain the generator geometrically. What I like to do is, in some sense, generalize this computation. In fact, this generator will come into play at the end of the talk, and I hope by the end of the talk, it is clear what I mean by we're going to try to generalize this. Okay. Okay. So let me just introduce briefly something that already came up in a previous talk, which is the space of commuting and tuples. For this talk, I'm just gonna not write it down for commuting tuples. So basically, what we're gonna do is, if we have a compactly group, what I'm gonna be taking a look at is you have pairs of elements in G, and you require them to commute. G1 times G2 equals G2 times G1. And then you think about that guy as a topological space. How do you do that? Well, that's quite easy, because the way this is set up, this is naturally a subset of G squared, and G squared is a smooth manifold. You have a smooth manifold. Inside of it, you have a subset. You can endow it with the subspace topology, and you say, okay, what can I say about that space? Okay. Turns out that when you have a compactly group, this guy is real algebraic variety. That's actually quite easy to see, because when you have G a compactly group, you can see as an algebraic variety. So you have some defining equations, and then basically what you have to do is you have to impose further equations that are coming from this relation. So that's not hard to see. The basic question is, what can you say about that guy? What can you say about the multiple groups of that guy? That's basically the question that we're gonna try to tackle today. Now, there is a natural action of G on, yes?
Is this a question you can still ask for a lot?
Indeed.
Yeah.
Indeed. It doesn't have to be a linked group. You can say that G is any topological group, and the question is the same, right? I'm going to ask it to be compactly grouped because we have order structure. And in more order, we have the three default that I described. There is a basic observation, which is, you have an action of G by conjugation. Namely, if you have a commuting pair and you conjugate that pair by the same element, that still commutes. So that's quite easy to see. And the quotient space is called the space of representation. Okay, so you commuting pairs mod up by the conjugation action. And this guy is actually a meeting point between different subjects in math. And one of the reasons is that this guy represents the modular space of flat connections of principal G bundles over the torus as well as S1. So this is actually a well-known result in differential geometry. On the other hand, this does appear also in algebraic geometry in the following way. If you ask G to be simply connected and simple, then this space of representations, you can identify it with the modular space of semi-stable principal bundles over an elliptic curve with structure group the complexification of G. And that gadget has been studied quite a bit from the point of view of algebraic geometry. So we have topology, differential geometry, algebraic geometry. Actually, this also comes up in physics that I've already mentioned. So this is a meeting point where different people meet. And so this gadget has been studied through many different points of view.
I have a question. Yes. How about the cohomology ring of the space of the meeting?
That is another problem. Yes, it's really hard. Really hard. In fact, for the unitary groups, it appears to be the case that.
I mean, what's the open problem?
That's what you say, no? Complete. Just for the unitary groups, it appears that you obtain inside of the cohomology of the symmetry group with all possible representation. So that kind of problem says that it's really hard. But you're welcome to think about it. With me, I mean, I'll be really, I've been trying to think about that for a long time. Anyhow, so we have two spaces. We would like to say, okay, what can you say about the homotopy group? That's the basic problem. Okay, that's the basic problem. Let me start by thinking about pi zero. So what is pi zero? Connected components. And I do want to say that for pairs is easier than for entities. So I'm just going to think about pairs. There is a well-known result in compactly groups theory, which says the following: if you have a compactly group whose homotopy group whose fundamentally dispersion free, then the centralizer of any element is connected. That is well known and appears in group axis group or whatever your preferred reference is. But what that means is right away that tells you that these spaces are path connected if you have a compactly group that is whose fundamental group is free. And the reason is quite simple, because if you choose a commuting pair and then you want to move it around without leaving commuting pairs, so one idea is, okay, I fix the first component and I move the other component. As long as I stay within the centralizer of the first component, I'm good. But that guy is connected, so I can connect it within a path to the identity. And then I connect my original pair to x, 1. And I'm on business because now G is connected, and then I can, when I have 1 in the second component, then I can move x to 1, and then we're good to go. Everybody is connected to 1, So that actually tells you that this guy is path connected, and it's easy to see that this guy is also connected because the quotient map, when G is connected, it induces a bijection on pi 0. So first problem solved is path connected. Good. What can you say about pi 1? It turns out that you can say something nice. And in a joint work with Alexandra Peter and Juan Soto, we proved that when you see the inclusion of commuting pairs inside G square, well, this is actually quite smaller than G square, but as far as pi 1 goes, it turns out that this inclusion gives you an isomorphism in pi 1. Okay. So what that means is that if G is simply connected, then this guy is 0, so this guy is 0. Okay, here I have a mistake. I mean, it's not a mistake, double something. It doesn't matter. So in particular, if G is simply connected, then commuting pair is connected. So pi 0 is taken care of, pi 1 is taken care of. Good. So the next question is, what can we say about pi 2? Okay. So what can we say about pi 2 of this guy? What can we say about pi 2 of this? Okay. So let me start with the representation, which is in some case the simplest case, and what is well known for algebraic geometry. I just didn't know that when I first started. So what happens is that when G is simply connected and simple, we can use that identification that I mentioned before with semi-stable bundles over elliptic curves. And then what happens is that that problem of thinking about the representation space has been studied by the other algebraic geometry people. In particular, there is a theorem of Jenga and so on, independently by smaller people, that tells you that this guy is actually homeomorphic to a weighted projective space. Okay. So let me just spend a few words about how you construct a weighted projective space and how you get a weighted weighted projective space you get in this case. Okay, so so let me start by recalling the definition of weighted projective space. So let's just remember how you construct the projective space. So, but basically, what you do is you look. You can do this with this already came up in many talks. You can do the CR plus 1 minus 0, then you define an equivalent relation, or you can do with the unit sphere. Those two things are the same. So let me just work with the unit sphere inside of CR plus 1, and inside of it, I'm going to define an action of the unit circle. So the typical action for CPR is you take a complex number of norm 1, and then you multiply it by each entry by that guy. And the quotient of the sphere modified by that action is CPR. But in a weighted projective space, what you do is you modify the action by putting some weight. So in each coordinate, so you have an r plus 1 tuple of positive integers. You can change the action in each coordinate by putting an exponent, and the exponent is going to be a positive integer. And then if you put all integers to be equal to 1, you record the honest to God CPR. So this is a generalization of the complex projective space. So this quotient is what I'm going to denote CPW is the weighted projective space. And what happens is that the representation space can be described in this way. I just have to explain you which weights you use. And for that, you have to go back to the geometry of the Lie group, namely the root system. Let me just say a few words about notation. So if you have the Lie group, then you take the Lie algebra, and then you can complexify it. And then inside of the complexification, you got a Cartan algebra. Now we're working with complex coefficients. So this will be the complexification of the Cartan algebra is going to be a Cartan algebra now, the complexification of G. And then for each root, you have the corresponding core root, right? And then what happens is that you pick a set of simple roots, and then you look at the lowest root, the corresponding core root, the negative. So this will be so this negative makes it this guy on the left hand side the highest core root. You can write down as a linear combination of the core roots associated to the simple roots. Turns out that those coefficients are integers, and they are the so-called core root integers. And then I'm going to set up, for simplicity, the n sub 0 to be equals to 1. So in fact, these gadgets, for those of you that think about twisted K theory, these core root integers came up surprisingly in a famous theorem by Bredon and Telemann, because they computed the twisted K theory of G acting on itself by conjugation, and then there was a shift that appeared there, which was the dual constant number, which is the sum of these core root numbers plus 1. So if you add this guy, then it will be the sum of all these core root integers. Anyhow, why am I talking about this? The reason I'm talking about this is that precisely. Before I say that, and this is going to be important later. I'm just, for your reference, I'm just going to show you what kind of numbers appear for the different simple groups that you have. And so these numbers can be refuted, but the surprising thing is that when you do this for any compactly group that is simple connected, you only have these options. So again, this get to be repeated in some cases. So for example, for the especially third groups, all numbers are 1. But what is important to observe here is that you only get integers from 1 to 6. You don't get anything higher. In particular, the only primes that are involved here are 2, 3, and 5. Now, the reason that I'm talking about this is that precisely Lojenga's theorem says that the representation space, the modular space of the semi-stable bundles over the elliptic curve is precisely a weighted projective space where the weights are precisely those core root integers that I mentioned before. I do have to say that I'm a bit puzzled about how you go from here to here directly. So there should be a simple way to go from the left to the right, but it is supposed to be a homeomorphism. I know how to do it by homotopy equivalence, but there should be a transparent way to go from here to here. I haven't been able to find it. So if somebody knows how to do that, I'll be happy to hear it. Because this is not something crazy. This is just at the end of the day, you can rewrite this as 2 copies of t squared. Then you have to modify the diagonal action of the value, and then it turns out to be a weighted projective space. There should be a direct way to go from left to right. The way I obtained this is Lojenga's and the people from algebraic geometry do a lot of reductions, and then at the end they get to the weighted projective space. But you have to travel too many roads, and I get lost. So I don't really know a way to go from here via homeomorphism. I do know how to do that via homotopy equivalence. In any case, why am I talking about this? I said, okay, let's compute homotopy groups and yes.
Do you expect the same company to change 2 by 3?
No.
No.
It's already not that. So 2 is really special. Once you move, then it's not longer true.
But it's still a variety.
Yeah, but it's it's not gonna be connected in some cases. I mean, so that's already a problem. And more than that, you don't have a like
It's pretty interesting.
this is so the case n equals two. So commuting pair is way easier than commuting triplet. Yeah, sure.
I guess L2 is acting on B squared.
I do not understand that. But it would be nice to. So would you like to know the quotient or by that action?
That was the action, the right hand side.
I don't know. I have no idea. I mean, I don't know how to go from here to here. Directly. But that's actually a really interesting question. I mean, there should be a natural action on the right hand side, but I don't see it. I mean, I don't see it. Anyhow, why am I saying this? Because I said let's compute homotopy groups of unit person G in the representation spaces. Well, with this, we're good to go in the representation space because those weighted spaces are simply connected. More than that, Kawasaki computing the homology of those weighted predicted spaces. Turns out that the homology of the weighted predicted spaces look exactly like the homology of the good old predicted spaces. That is to say, the homology of the weighted predicted spaces are given are concentrated on even degrees, and there are copy of set until degree 2r, where here r is the rank of degree. So as far as homology goes, you can forget that was a weighted predicted space. And with this, we're good because it is simply connected. The second homology is set, so that means that the second homology group of the representation space is going to be set. Okay. So pi 0 is trivial because it's not connected. Pi 1 is trivial, and pi 2 is. Okay. Good. So now let's go back to the original problem. How do you compute pi 2? By the way, you can do this for any compact big group by reducing to the case of simply connected with simple A groups, because you can use the usual classification results of compact big groups. So if you are interested in pi 2, it's easy to reduce it to this case. So I'm not losing general here. So let's go ahead and tackle the original problem. So how do you go and do that? So as I said before, if you suppose that G is simply connected, then this guy is simply connected. So then using that, you can reduce the problem to compute the homology, just like we did for the representation space. Okay. First reduction. Forget about homotopy groups. Look at the second homology group. Okay, so that's probably easier because you have some tools that you don't have here. Okay. Good. First reduction. Now I'm gonna do something that is kind of weird because you usually would do the other way around. So you have the conjugation action of G on commuting pairs. So you can do the Bredon construction. This is a classical object. This is something that any homotopy theorist will think about. And then the Bredon construction fits inside a nice vibration where the base space is the classifying space of G, and the fiber is the commuting pairs. But what happens? This guy, if G is simply connected, we already said that pi 0 is trivial, pi 1 is trivial, pi 2 is trivial. So this guy is actually 3 connected. But BG is 3 connected. So if you look at the cell spectral sequence, And if you want to look at total degree two,
Why spike?
because if you look at the vibration given
Oh,
by
I see.
G, E, G, G, and the homotopy groups are shift. But we don't need that, but what I'm saying, if you look at, you write down the spectral sequence in total degree two, there is only the bit that appears from here. There are no differentials, so everything is good. So then it turns out that the second homology of the commuting pairs is the homology of the Bredon construction. This is something weird. Nobody would think about doing this. You usually would go from right to left. You would only do this if you're desperate enough. Which was the case. So you asked me about homology. So, so even in Mexican homology, straight up, it's not easy. So if you're desperate enough, then you think about other ways, and then we went this direction. Now, why would you do this? So it turns out that you do have some additional tool to compute this Borel homology. And is the following reason. So in general, if you have a compactly group, you can show that commuting pairs is a GCW complex. That's actually not what you see. In fact, you can describe an explicit GW complex structure, and that is not hard to do, because if you think about, in this particular case, every commuting pair turns out to be conjugated to one that lives where both components lives in the maximal torus. So it turns out that in this particular case, it's enough to work with T squared, and if you give that guy a WCW complex structure, you can extend that to a GCW complex structure and commuting pairs. But what is good about this is that T is a smooth manifold, and WX will be on it. So that you can actually, just by looking at that result, then easily you can construct a CW structure on T squared. But you can do this by looking at the geometry and the root system. You can actually produce an explicit WCW complex structure. Now, the reason that this is useful is because now you have a Bredon spectral sequence type that computes the Borel homology. So you have a spectral sequence that you can run, whose second page, so the E2 page, would be the G equivalent Bredon homology of commuting pairs with a local coefficient, and the local coefficient is given by, if you have a cell of if you have an orbit of the form G mod K, you have to take the homology of the clarifying space of K. So K here is the isotropy. So let me stop here for a second. Let's try to understand what's going on. So I have to look at the GCW complex structure, and so the cell will be of the form G mod K times e to the n, and to each cell I have to compute the homology of the isotropy subgroup, the clarifying space of the isotropy subgroup. So that doesn't sound easier than computing the homology. That doesn't sound easier. And in degree 2, you can do it, but in higher degrees, forget about it. So here I'm just telling you how you compute the Bredon homology spectral, the Bredon homology. You obtain a GCW complex structure. You obtain, you form an actual chain complex, which is, you choose a representative for every cell in dimension I, and then you look at the homology of the corresponding, or the clarifying space of the corresponding isotropy subgroup. Okay, good. So how are these isotropies of groups? So the isotropies of groups are precisely the centralizer of a commuting pair. So basically, this problem leaves you to understand if you have a commuting pair, you look at the elements that commute with both elements, that's going to give you a subgroup of G, and you have to take the classifying space of that guy, and you have to compute the homology. Okay, so then you just think about that's what you have to think about. If you want to say something about the E2 page of this spectral sequence, what you need to understand is what can you say about the homology, the classifying space of the centralizer of a commuting pair. Then there is a big problem, which is annoying, and this is what makes this. So this is the hardest part of this computation, and we spent a long time on it. Do remember what I said before? If G has pi1 torsion free, centralizers are connected. Okay, good. Our assumption is that G is simply connected. Oh, sorry about this. So because of that, the centralizer of one element is connected. Okay, good. But we don't want to think, we are not thinking about the centralizer of one element. We're speaking about the centralizer of two elements that commute. So there's a little trick. If you commute with the two of them, then you commute with the first one. So that means that you're in the centralizer of the first one. And then inside that group, you commute with the other one. So it's like an inductive. But here's the problem. The centralizer is connected, but the centralizer can have torsion with pi1. So that means that this guy doesn't have to be connected. And that's happening with the next. If in the cases that this guy is connected, lag is simple and then you're good to go. But in this computation, this is what makes everything really tricky. So what you need to say is, what you need to understand to pull this off is, what can you say about this group? What can you say about pi 0? And the first thing you learn after digging a lot of books is that, okay, this guy may have torsion. The pi1 may have torsion. What can you say about the torsion? And it turns out that you can say stuff about the torsion using the quantum integer. So let me just say a few words about that. So if you have the inside the Cartan algebra, you can look at the closed alcove that contains so you have to fix a simple roots. Then the simple roots give you a Wald chamber. Inside that Wald chamber, you can look at a Wald alcove that contains 0. So that's going to be a simplex. And then in that simplex, there's going to be another dimensional simplex that is cut up by you look at the simple roots equal to 0, and then you look at the lowest root equals to -1. And then what happens is that, first of all, every element in a simply connected Lie group is conjugate to the exponential of somebody in that alcove. Okay, so you may assume that it's of this type. And second of all, you can, when you have it in this form, you can say how the portion of pi1 of the centralizer is depending on which walls the element x tilde lives in. So if it's in the interior, there's no problem, it's connected. But depending on the walls that that x tilde lives in, you can say something about pi1. And that's basically what happens is that you can say that pi1 of G is always going to be a cyclic group of order, the greatest common divisor of all these guys, the co-root integers, where x does not live in the corresponding wall. But let me remind you again that these numbers can only be 1, 2, 3, 4, 5, 6. Okay. So in particular, this guy, then what that means is going to be a cyclic group of order and most 6. Okay. And then with some effort, you can prove that the components of a commuting pair, you can see that sit inside pi 1 of the derived group of the centralizer, but what happens is that this guy is a cyclic group of order almost 6. So this guy is a cyclic group of order almost 6. So this is
What's the derived group?
it's the square of n itself,
The square of what?
the commutator of n itself.
Oh,
So basically, you're removing it had center, you have a bit center. That's one way to do it. Anyhow, this is a bit technical, but with some effort and a lot of pain, you obtain, okay, this is what you can say about pi 0 of the centralizer. So it's going to be a cyclic group of order at most 6. And that is going to be key. Okay, so let's go back to the Bredon spectral sequence. So let's look at the E2 term. So I should have put. Sorry about that. So let's go back to the spectral sequence, and I'll show a picture later. So I'm interested in total degree 2. Total degree 2. So there are 3 possibilities: p equals 2, q equals 0, p equals 1, q equals 1, and p equals 0, q equals 2. So let's think about q equals 0. In that case, the coefficient system is trivial because you're looking at H0 of the classified space of the isotropy, but the isotropy is connected, but B of the isotropy is connected, so that's going to be trivial. And whenever you're working with a trivial coefficient system, the Bredon homology is just the homology of the force. Oh, but that we already know. That's a way to take space. So we know the homology of that bit. So in particular, E20 is going to be Z. So this is how the spectral sequence looks like. So remember, we're interested in 12 degrees 2, and also the differences that make line. So basically, what we just figured out was this line. So for what we care about is so Z0, Z0. So this 0 is good because it doesn't hit this guy. So we already have a contribution of Z. So we are left to figure out this group, and this group. If we can pull that off, then we can say something. Turns out that we can say something, which is kind of surprising. Again, this is after hitting your wall, your head on the wall for about a year. Only to compare to. Okay, so let's look at Q equals 2. Q equals 2. That case is easy because you only need to worry about the 0 part. So if you write down the chain complex that computes Bredon homology, and then you observe that the isotope, the action of G on the 1,1 is constant. With that observation, you are able to show that that guy vanishes. So with some effort, you're able to show that guy vanishes. I'm not going to talk about that because you just write down the chain complex, and it's easy to show that this guy is 0. So this is how the spectral sequence looks like. So here is 0, here is 0. So we are left to compute this guy, and this differential. Okay. And this is the most technical part, and I probably don't want to talk about it too much. Let me just say a few words. I'm gonna go fast in this part. This gets too technical. So again, we just have to compute these Bredon homology groups, this guy and this guy. And it turns out that you can do that with a lot of effort. And the key idea, so let me just say what happens if you're gonna do the coefficient system at an orbit of this kind. Basically, you have to look at the first homology group of the classifying space of the centralizer, which happens to agree with pi 0 of the centralizer, which we know is the group, but we don't know which one it is. And as the tuple moves, that changes drastically. It doesn't change continuously.
But are they simple?
No,
They have finite.
no. You can have a set over there.
Oh, okay.
So this is quite tricky. So you have to compute. So with some effort, we were able to say that this is a liquid group of order almost 6. But now you have a chain complex where in that chain complex you had to put a bunch of copies of these liquid groups, and then you don't know what they are, and you have to compute the homology of chain complex that you don't know what it is. You know something, but you don't know what it is. So at this point, this seems hopeless. So the main idea is to work one prime at a time. And then basically what you do is forget about it, man. Don't work with all of it. Just look at tuples where you have certain time popping up in pi 0 of the centralizer. And it turns out that this guy, if you look at it, is a subcomplex, a GC level complex. And the reason that this is good is because if you look at the table that I showed you before, you look at the only in these two cases, E7 and E8, you get square root of prime. You only have 3 primes, 2, 3, and 5. And only in these 2 cases, you have a repeated prime. So basically what one is doing by looking at this is looking, okay, let's look at the pairs where the path connected components are non-trivial. And that turns out to be a subcomplex. Okay. And the good thing is that the Bredon homology, the Bredon homology that we're interested in, you can rewrite as the sum of working one prime at a time. And the good reason about it is that if you don't work with E7 or E8, which is a problematic prime with E equals 2, then what happens when you just look at this guy where this prime is popping up, then over here the coefficient system is going to be constant. In which case you obtain the homology of the quotient. And the key point is that this quotient also is locally enough a weighted projective space. So this is what, so basically the weighted projective spaces are what save us. Because you already know the homology of this guy, and it's concentrated on degrees, or on even degrees. So with some further effort, so that's for everything except for E7 and 8. And with that, you get to show that this guy is then 0. And moreover, you're able to show, I'm not going to tell you how you do this, with some further effort, that you're going to get a cyclic group of order D, where D is what is called the Dynkin index, which is the lowest common multiple of the closed integers. So this is actually a number that comes up in representation theory. But then let me just show you how the spectral sequence looks like. So you have a copy of set that comes from the way to predict spaces. This guy turns out to be zero because it's you can rewrite it as a direct sum of homologies of some other way to predict spaces. This one was simple to show that it was zero, and this guy is a cyclic group of order B. So this set has to survive. In fact, this map turns out to be surjective. And then you can handle the other cases in a similar way with more effort and pulling all of that together. So let's look at the spectral sequence. In total degree 2, you only have this. There are non-trivial differentials that can, so this is already zero, nothing to say. This is already zero, nothing to say. This goes to this guy, but this is a cyclic group, so a copy of set is going to survive. In fact, this guy is projective. Nothing else can happen. From here, there are no more trivial, non-trivial differentials. So this is going to be in total degree the infinity page, total degree 2. This is the infinity page. And there are no extension problems. And then with that, you are able to say the following, which is the main theorem of this talk, which is the second homotopy group of the commuting pairs in a simply connected or simple compactly group is isomorphic to set. Moreover, so we remember we had computed the second homotopy group of this guy using the identification of it as a weighted projective space. So you also get phi 2 is going to be set. Turns out that the function map is not an isomorphism. Instead, it's multiplication by this Dynkin index. Okay. So let me stop here for a second. Let me go back to the beginning of the talk. So I said, okay, you have G a compactly group that is simple and simply connected. And we said, okay, phi 3 of it is isomorphic to set. Phi 3. And then I gave you some geometric generators. Now we're talking about phi 2. So it doesn't seem to be the case that these two are connected, but they are. And this is how I'm going to finish. So first of all, can I write here? So let's look at the case of SU2. So these are 2x2 matrices that are unitary and have determinant 1. Inside of it, you can pick a maximal torus, but that guy is easy. So if you look at the maximal torus given by diagonal matrices, but they have to have determinant 1, so they have to be of that form. They have to be unitary, so they have to be in S1. So this is a copy of the circle. Okay. Now, the representation space of commuting pairs is going to be, in this case, homomorphic to T square modified by the diagonal action of this value. That just says that any commuting tuple can be conjugated to a diagonal one. But then you have to modify the action of W by the diagonal action of W. But in this case, W is a cyclic group of order 2. So this is not too hard to imagine. You have 2 copies of S1 and you modify an action of SEMO 2. You have a torus. Inside that torus, you have an action of SEMO 2, and you have to do the quotient. You gotta think about how the action is. And in each circle is the conjugation action. You have set cross set, and in each circle you put the conjugation action and you multiply that. So the way I like to think about that is, so S cross S is a torus, And the way the action does is you think about that as a donut skewer. You put a skewer and then you flip it around. And 2 points are identified. If one point and you flip it, they're identified. So basically, it's not too hard to see that a fundamental domain for that action is that if you cut the donut over here, so you pick one of the sides, that's going to be a fundamental domain, and inside that fundamental domain, these guys are identified. You have a pivot case, exactly. So that guy is homeomorphic S2. So for SU2, that guy is homeomorphic to S2. We already knew that because it's supposed to be a weighted projected space. It's actually CP1. But this description is easy enough. Now, what happens is that you can use this to obtain a geometric generator in a simple way. So we basically with that description, you know that the quotient is S2. So you can force things in the following way. So you have commuting pairs, and you would like to get a generator for phi2, but you happen to know that the quotient is a 2 here. So if I'm able to get a map from here to here such that the composition has degree 1, knowing that this has phi1 set and this also has phi1 set, if this composition has degree 1, I'm good to go. It has to be a generator. But I know inside commuting pairs, you have a copy of S1 cross S1. So basically, what you can do is you can construct by hand easily a map from S2 to the torus, such that when you compose with the quotient, you get a map of degree 1. So that has to be a geometric generator. So you can do that by hand. Yes, but it is, however, what I'm saying is, okay, what am I saying? Let me put it this way. Sorry. This probably will be better. So you can construct a map from here to here by hand, such that when you quotient by the conjugation action, you get a degree map, a degree 1 map, right? So this has to be, in that case, a generator for pi2 of this guy, right? Because this guy would be a generator pi2 of this guy, and this guy is set, so it has to be a generator. So that's what I want to say. Now, once you have that, you can compose with the generator for pi3. So basically, the basic observation is when you compose with the generator of pi3, which happens to be a homomorphism, then you obtain a generator for pi2 from commuting pairs. So after doing all this work, you realize that this depends on the geometry of the root system of the group. So that gives you the feeling that maybe we took the way longer road to obtain this, but honestly, I don't know how else it can be done. So with that, I'm going to finish. So thank you so much for your attention.
Question, comments?